Hello everyone, my name is Shashank Gupta and I'll be presenting my paper titled Feature Extraction Functions for Neural Logic Rule Learning. So this slide provides an outline of this presentation. We have an introduction section which provides a context of the problem statement and formulates the problem statement. The proposed method provides the solution for the problem statement. Evaluation section provides details about the experimental design and the results obtained. Conclusion provides a summarization of the work done and future work that is planned to be done. So currently the transformation from input to output through a neural network cannot be explained in a meaningful manner, which makes the existing neural networks equivalent to a black box systems. In a black box systems, we have an input which is transformed through a series of processes or steps into an output, but the system cannot inherently explain as to why the certain output has been produced given a certain input. Now the question is why this problem occurred for neural networks. Broadly speaking, the training process is essentially absent of any direct or indirect human intervention. As we can see from this diagram, the user just provides the training data at the beginning of the training and do not have any control over the optimization process, which yields in a trained neural network. So essentially there is no mechanism to guide the model to a specific rule or specific pattern which we derive from our own expertise about the specific problem. So the black box problem in neural networks needs to be solved mainly because due to absence of any causal explanation for the output given a certain input makes the system untrustworthy. If the system becomes untrustworthy, it cannot be used in critical domain sectors such as healthcare, power systems, where there is a very low tolerance for failure. Also, purely data-driven learning can sometimes lead a model to learn some unwanted patterns or functions. To solve the problem of black box in neural networks, we can combine human knowledge represented in a symbolic form with neural networks. Combining human knowledge with neural networks will result in a special class of networks called neural symbolic networks or neural symbolic systems, which can provide a rule-based ante-hoc explanation for the output given a certain input. To construct a symbolic system, we have two sets of approaches. First one is the augmentation approach, where we encode the symbolic knowledge into the trainable parameters of the neural network. Iterative knowledge distillation is one such framework which provides a mechanism to encode the human knowledge, abstracted as first order logic rules specifically. Second method is the pipeline approach, in which the human knowledge is applied as a series of logical steps to influence the output of a neural network. Our proposed method is a pipeline-based approach, which we call it as feature extracting functions. They transform the input data distribution of a neural network, analogous to a data preprocessing step. This slide shows an overview of our proposed method. We have two sets of inputs. One is the input training data, second one is the knowledge. The knowledge and the input data are transferred to a set of programming functions called feature extracting functions. These functions output a modified distribution of the data, which is then given as input to a neural network for training. So this slide provides an example-based explanation of our proposed method versus the augmentation-based method and a simple normal CNN neural network, which is devoid of any logical or human knowledge support. We can summarize the training process of our proposed method similar to a same training process of a general purpose neural network, where we have input as the training dataset and the feature extraction functions constructed from logical rules. While every iteration we transform the training dataset using feature extracting functions and provide the transformed dataset as an input to the neural network, which optimizes on this equation, which is a normal log likelihood optimization function. We test our proposed method by comparison with the iterative knowledge distillation, which is an augmentation-based approach on the task of sentiment analysis for three public datasets. First one is the Stanford Sentiment Tree Bank dataset. Second is the movie reviews dataset. And the third is the customer reviews dataset. So this slide shows the results obtained for the task of sentiment analysis using our method CNNF versus the CNN rule, which is constructed from iterative knowledge distillation, and the CNN, which is the base network devoid of any human knowledge support. As we can see from the results, our method performs quite well for the task of on the datasets SST2 and movie reviews, but lags behind on customer reviews, but by a very small margin. So to summarize, we provide feature extraction method as a pipeline-based approach to construct neural symbolic systems. Our method provides a mechanism to accommodate the dynamic nature of knowledge, unlike the augmentation-based methods like iterative knowledge distillation. As we show from the experimental results, our method performs better than the knowledge distillation-based methods. For the future work, we would like to perform an ablation study in order to highlight the effectiveness and limitations of our proposed approach. Secondly, we would like to assess the overall applicability of our proposed method, constructing more rules like we constructed for A but B syntactic structure and more knowledge constructs. Third, we would like to perform an extensive sets of experimentations for multiple tasks and compare with a range of existing neural symbolic systems. Thank you very much for your attention, and for more information, you can contact me on my email ID. Thank you.